me? And
Yes.
yes, okay, great. So it's a great pleasure for me to be invited to speak on this topic here in this conference. And as everybody else, I regret to not be able to be there in person. So hope that will work next time. So I'm going to talk about battery diagnostics, but just to set the stage for this topic, let me maybe remind everyone that everybody, I think almost everybody has a smartphone, and so everybody who has a smartphone is acutely aware of all the things that matter for the end user in terms of what it means to have a good battery. We want a battery that holds a lot of power, can last a long time, and that we recharge quickly, and that is also safe. We don't want it to overheat or blow up. And those same issues, I mean, a lot of people don't own electric vehicles, obviously, but if you have a smartphone, you can just translate all your knowledge to what it means for having a good battery in an electric vehicle. You want a good driving range. You don't want to recharge it all the time, and you want to be able to recharge it quickly, and you want to operate it safely, of course. There is one important, really important issue that is a little bit different for an electric vehicle from a cell phone, and that is the cost of the battery. So if you buy the electric vehicle, really you're buying the battery for the majority of the money. And that is important if you buy a new car, but it is even more important when you plan to sell a used electric vehicle. How is the new buyer going to know whether this is a good battery? And I'm pointing all this out because that really highlights the issue of battery diagnostics. What do we do if someone gives us a cell and we want to know how good the cell is? What might have been its history? Do we know what the capacity is without discharging and recharging it? Do we see certain unusual behavior? Can we foresee any failures in the future? And at present, that is really an area where that is significantly lacking. And this is an area where we wanted to address. So there is a big field by now of in situ and operando techniques, including NMR and MRI, to study cells under operation. And the majority of these, including typically in situ NMR and MRI, can only be done on cells, on research cells that are built for the precise purpose of studying a particular mechanism, or maybe evaluating a particular battery chemistry. But what we really need is sort of the in real life situation, as I have pointed out. Someone gives you a cell or a used car, and you want to know how good the battery is. So we would like to have a technique that can tell us something about the cell non-destructively, quickly, and in an actual commercial type cell. So we want to be able to predict battery failures, predict lifetimes, predict them early, non-destructively, and quickly. Now, this is sort of the goal. I'm not saying this is we have the solution right now, but this is the direction in which we're going. And we recently developed an MRI technique that can provide new observables for battery diagnostics. Now, MRI is, of course, well known in the medical field and less well known in the materials field. And so the main challenge that one faces immediately at the first step, if you want to apply this technique, is that the radio frequency irradiation that you need for MRI cannot penetrate the conductive casing of a cell, and it cannot easily penetrate, even if it could penetrate that, it couldn't easily penetrate the thin layers between the electrodes in the stacks. So that was a big challenge that we that has that has posed lots of problems for us for a long time, until we realized that we could actually learn something about the battery without having to get the radio frequency inside. So, and this for this reason, we call this technique inside out MRI. And so let me illustrate how this works. So I hope you can see the laser pointer here. So here's a pouch cell. We put it into the battery holder, and the whole thing goes into an NMR probe inside the NMR machine. And outside of the battery, we have these compartments which are filled with what we call detection medium. And this could be, in the simplest case, just water. Actually, water works very, very nicely. Everything is sealed, so the cell never gets in direct contact with the water. So this could be water or some other detection medium. For example, recently we actually have done it with a solid as well, with a slightly different technique. And then what we do is we acquire magnetic field maps. This can be done. This is actually quite well known in medical MRI as well. We acquire magnetic field maps through this compartment here. And why would that be of interest? So if you put a cell in a magnetic field, you're going to have lots of components in your battery that have a given magnetic susceptibility, paramagnetic or diamagnetic. And it's quite well documented how many active battery materials change their magnetic susceptibility properties depending on how much lithium you have, for example, in the cathode. So there's magnetometry work, for example, from Stan Whittingham and others who have well documented this. So that means we have, in principle, a direct connection between microscopic properties and these macroscopic properties that we can measure outside of the cell with this inside-out technique. And here are then examples of such measurements. Now, to remind, I'd like to just remind you this white space here, that's where the cell sits. And then we acquire signals from the detection medium outside of the cell. So this is inside out MRI. And we discharge the cell here with the indicated discharge capacity here. And the magnetic field maps change significantly. They get more intense here, and also the distribution of magnetic fields measured changes. And then we go back, we can actually almost get back to the initial state here. So one can then examine different types of cells and different cell material. For example, if you take cells made with NMC cathodes, you get this effect. If you discharge the cell, your magnetic susceptibility actually increases. And if you take LCO, the magnetic susceptibility decreases. So what matters is that you don't need every material to go along the same curve. You just need to know what the trend is for a given material. And then you can determine, for example, in this way, you can determine in a one-point measurement, you could determine the state of charge of a cell. And not just the state of charge, because this is just the total value that's plotted here. You could also determine a distribution of state of charge. I'll show you an image a little later about that. So next, we wanted to examine, of course, we would like to be able to detect defects, as I pointed out. And we took as inspiration, for example, the Samsung press release on what types of defects they found. And then we asked the Battery Prototyping Center at RIT to make cells for us that had these defects incorporated into them. And here are some results of these magnetic field maps. We have cells here that have missing parts, for example. We have cells that have extra scraps incorporated into the stack, something that actually does happen during cell assembly when you have cutting and you have parts floating around in the atmosphere. And or we have cells in this collection that had folded electrodes. And these magnetic field maps, they often even just visually give you a very direct clue of something not being quite right. So these measurements are quite sensitive. But also then, of course, you can, rather than inspect them visually, you could apply statistical methods such as maybe principal component analysis that we have done here. So since we're measuring magnetic fields, we can also look at other mechanisms that produce magnetic fields, for example, electrical current. So with the same measurement, and the only change we need here is really we do the measurement while we charge or discharge the cell. So the previous measurements were all done during the resting state. But if we do this while the current is on, we can also sense the distribution of electrical currents and how it changes over the charge cycle. Here, I'm just quickly giving you a survey of some of these results. So if we look at this rightmost panel here, this is a cell examined during charge, a healthy cell, and we combine that, we compare that to the measurement after damage. So after damage, we see a clear highlight where the damage occurred. And this is an example of how this electrical current sensing can help you in diagnose different types of defects. I also just wanted to give you a brief survey of very recent results, many of them just this year, of extensions to this method. For example, many cells, many iPhone cells, and it's probably true, it's definitely true for Samsung as well, have fairly strongly magnetic components in them. And an example would be just, for example, nickel tabs or something like that. And they create, of course, because we're measuring the magnetic field, they create perturbations in those measurements that we really would like to rather not see. And we have a technique that allows us to deal with these distortions and to get accurate readings of the state of charge again and electrical current distributions. Recently, we've also been able to get the radio frequency inside a battery cell. I don't advocate this as a fast technique or a very particular sensitive technique, but it could be a very good research technique. And we have been able to measure electrolyte lithium, intercalated lithium, and metallic lithium with this technique. We also now have an ultra-fast, what we call ultra-fast technique. We can do the measurement and classification in less than a second. And recently, we've also studied large format cells, in this case, 50 amp hour cells, actually in an MRI scanner at the medical school. And also here is some recent work on AC imaging. So instead of sensing DC magnetic fields, we wanted to sense alternating magnetic fields. And that would be of interest when we want to do something that is similar to electrical impedance spectroscopy, except in a localized fashion. So we have a cell here, and we want to measure in different locations what is the change in amplitude and ideally the phase of the magnetic field that we see in different locations. So that would be a form of localized EIS, just in a contactless fashion. Very quickly, because I don't have that much time, I also want to tell you about the other technique that we have co-developed recently, the use of advanced magnetometry sensors for battery diagnostics. And this was done in collaboration with the group of Dima Butker and Arne Wickenbrock at the University of Mainz and the Helmholtz Institute in Mainz in Germany. And the main people who worked on this were Geoffrey Iwata and Yinan Hu. So, these people are experts in atomic vapor magnetometry. These are some of the most sensitive magnetometry sensors that are available in research, but also there are some commercial variants now. So you can measure down to femtotesla fields. So in this implementation, we put the cell in a solenoid coil shown at the right here, which produces this polarizing magnetic field. And then the magnetic field sensor rests outside of this arrangement, and the whole thing is contained in a magnetic shielding material. So with these measurements, we can get also these characteristic magnetic field maps, and this is as a function of discharge capacity here. And what is shown in the bottom row is the magnetic susceptibility distribution across the cell as determined from the magnetic field measurement. So we see, essentially what we see here is where lithium resides in the cathode in the cell. So with this work, so we have focused on these magnetic susceptibility measurements for diagnostics. Also, what we've done recently is measure electrical currents, and in particular transient currents during the resting state in the also during the relaxation period of a cell. So if you discharge, you stop, and then very quickly the current drops off. What happens during that period? That can be potentially quite interesting. And most recent work is on actually examining miniature solid state cells with this technique. So to summarize, I wanted to describe here some of the work we've been doing to address this in real life situation that I pointed out. So someone gives you a cell, you want to say something about it. How good is it? How long might it last? Is it safe to operate? And the two techniques that I pointed out were inside-out MRI and just very quickly at the end, magnetometry. And there are these new observables that become available with the techniques to the battery field, the measurement of magnetic susceptibility, the electrical current distribution, and thereby assessing the state of charge distribution and also state of health of cells. So with that, I want to thank all the people who were involved in this work in my group here, especially Andy Eilert, who started this inside-out MRI work, and Mona Mohammadi, who has done a lot of recent work. Stefan Wenders has done more on the magnetometry recently. And I want to thank the battery prototyping people for making these cells for us, and my collaborators at the Helmholtz Institute in Mainz, a group of Dima Butker, and especially Geoffrey Iwata and Yinan Hu for this wonderful collaboration in magnetometry. Thanks to all the sponsors, and thanks to all of you for tuning in.
Thank you very much, Alexei.